So we have the new procedure. The game warden distributes the participation cards and the notes. But as game warden, you give yourself 50 XP because you participated. You distributed stuff. So today's date is Wednesday, September 25th, 2019. Make sure you have your name and date written on your paper. So 9/25/19. So we are multiplying and dividing in polar form. We've already learned how to multiply and multiply and divide when we're in rectangular form, and it's kind of hard. You guys remember dividing in rectangular form where you did something like 3 plus I divided by 2 minus 7I, and you had to multiply by the conjugate. You had to do 2 plus 7I, 2 plus 7I, all that stuff.
No, yeah, I actually like that. That wasn't that hard.
It wasn't that hard. This is even easier.
No way.
Today is even easier than that. It's even easier than that because it's in polar form. Polar form is really good for multiplying and dividing. Rectangular form is really good for adding and subtracting. So here are the formulas. They look gross, but there it is. Say I have one complex number right here, and I'm multiplying it by another complex number right here. When I do that, look at what happens at their modulus, their moduli, I should say. R and S get, what happens to R and S?
They're together.
Yeah, they got multiplied. And what happens to the angles? I have angle 1, angle 2, theta 1, theta 2. I add them. It's that simple. Well, what happens if I go back here and I divide instead of multiply? If I divide, what happens to the modulus? Moduli. And when I look at the angle, the end.
Oh.
That's all of today.
No way. Wait, so
That's it.
Wait.
This is too good to be true.
That's it.
Can you review that again really quick?
I'll actually review it in words. The word formula. So the word formula is even better, in my opinion, than this thing because it's really hard to write out. Multiplying, if you're in polar form, then you're going to do what to the magnitudes? Quiet raised hand, quiet raised hand, quiet raised hand. I'm going to do what to the magnitudes. So look out here to the magnitudes. What happened to the magnitudes? Teflon. You got this. What is happening to R and S?
Oh, they're being multiplied.
There it is. Multiply. Multiply the magnitudes. And you're giving yourself 50 XP. Your card is now turned in. And then you're going to do what to the angles? Quiet raised hand. Chris?
I'm sorry.
You definitely add them. What about if you're dividing in polar form? What are you going to do to the magnitudes? Andrea?
Divide.
Divide. And quiet raised hand. What are you going to do to the angles? Eva? There it is. That's it. That's all of today's lesson.
Wow.
I caught it.
Wait, but so how do you actually do thing then?
What do you mean?
Like, how do you actually solve a problem?
We'll solve one. I'll show you. Today is one of those weird days where Mr. Sandell kind of goes and has a bunch of fun. I know that you guys could probably finish this in probably, I don't know, like a 5-minute homework assignment.
Finish your desk, can you play Risk?
I want to show you the most beautiful math I have ever seen.
Ooh. Oh. Okay.
It is what most mathematicians consider to be the most beautiful equation
How do you-
ever.
well, how do you
That's today's
consider
lesson.
math
That's
to
why I
be
like this
math?
lesson so much.
And
And there are lots of videos today, so that's also kind of cool.
You know what math even stands out for?
Can we play
Mental.
Mario Kart?
Oh, yes, 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 yes.
to humans.
So let's look at example 1. Let's assume that we're going to multiply by this z. This z is equal to square root of 3 plus I. Can everyone visualize where square root of 3 plus I is on the complex plane? It's in quadrant 1. Can everyone visualize where square root of 3 plus I is on the complex
Yes,
plane?
it's on that.
Quadrant 1, somewhere around there? Thank you, Eva. If I turn that into polar form, which you now all know how to do, if I turn this into polar form, it's 2 times cosine of 30 degrees plus I sine of 30 degrees. There's in degrees. I converted it for you. If I decide to multiply any number on the complex plane by this complex number, what is it going to do? Question, Chris?
Can I just ask a question really quick? Just off topic really quick. Please.
Okay, really quick.
Why is the mold like in circles then?
Oh, wait,
Or
that's not
the, or the rust or whatever that's called.
I think it might be mold. I have a general idea, but I'm not 100% sure.
Can you just give me a general?
I think like one area gets dirty, and then it kind of just spreads out from that area.
It's kind of nasty. Look at fill the.
Okay, coming back to the lesson. This is my favorite lesson. Chris, come back.
Okay, back to lesson.
So if we decide to multiply by this complex number in polar form, what is going to happen? If I multiply by z, that's going to scale everything by a factor of what? Looking at your polar form. It's going to scale everything by a factor of what? You have 2 numbers to choose from, guys. Thank you. And rotate by 30 degrees. By the way, the default rotation in all of math is counterclockwise. So I put counterclockwise. If I do a negative number, like negative 30 degrees, then that would be rotating 30 degrees clockwise. So negative is clockwise, positive is counterclockwise. CCW, counterclockwise.
I thought that's a cow for a second.
You can just add the, there it is. Now it's a cow. Yeah, so let's see what that looks like in terms of a video. Khan Academy, like, it has a lot of good things, but this is really, really nice. They talk about everything that's happening there. There's the formula that we just looked at. This is the same example that we just looked at. Square root of 3 plus I. Square root of 3 plus I. 2 cosine 30. I sine 30. There it is. What does that look like? This is what it looks like. If I have the complex coordinate plane, look what happens as a transformation.
Whoa. Wait a minute.
Again, when I multiply by that complex number, that's what happens. Every single possible number gets rotated and scaled. Look back at your notes that you just wrote. Everything is scaled by a factor of 2 and rotated 30 degrees. That is what is happening here. You are rotating by 30 degrees counterclockwise and stretching it. You're magnifying it by a factor of 2. Let's look at another one. Again, in order to find the magnitude, you take the square root of each number squared, and you get the square root of 2 over 3, which means if I multiply by this number, 1/3 minus I over 3, everything is going to be stretched by a factor of square root of 2 over 3, so everything is going to be shrunken because I'm multiplying by 0.471. And it's also going to rotate by 45 degrees. Let's take a look. If I multiply by this number, whoop,
What the heck? That is so weird.
let's try another one. Let's see what happens when I multiply by -2. You guys have multiplied by -2 before, I assume. Haha, funny joke. Okay. -2 has an angle of 180 degrees, and it also has a magnitude of 2. So I'm going to rotate by 180 degrees and stretch it by a magnitude of 2. This is really what you guys are all doing when you're multiplying by -2, but in complex land. Let's take a look.
Whoa, wait.
Again,
This is the same?
it rotates 180 degrees and stretches by a factor of 2. Again, it's really cool to think about. You've been multiplying by -2 your whole lives, but you never saw a geometric representation of what's happening on the complex plane. It's trippy, right? It's so cool.
We can put it full screen.
Yeah.
Is full screen this bad guy?
Oh, there.
Whoa.
Wait, play it again.
Let's look at another one.
Wait, no, play that one again.
Let's multiply with 1 marked. So if I multiply anything by 1, it's itself, right?
Uh-huh.
So let's start with, I think you're starting with 1. Oh no, you're starting with the actual complex number marked. Check this out. Hold on, let's full screen this guy. So if I mark 1 and I multiply by z, I should end at z. If I mark 1 and I multiply by z, I end at,
Oh, yeah.
Z.
let's check it out. Let's choose z to be right there and rotate. Let's multiply, I end right there. That was the same exact problem as number 1. This was square root of 3 plus I. Square root of 3 plus I. It's the same video that you saw before, but now I'm marking 1. I'm multiplying by this number right here. I'm rotating by 30 degrees, stretching everything by a factor of 2.
Can we do that? Can we put numbers in that thing and make it thing spinny?
I don't have the program to do this. Again, this is the same video that we saw before, but now 1 is marked. Let's try another one. We saw this one, -2, with 1 marked. There's 1. Where should it end up? If I multiply by -2, over there, -2.
Whoa.
There it goes. Ready? And whoop.
Whoa.
I really wish that my pre-calc teacher had the technology to do this. By the way, this is all from 3 Blue, 1 Brown. It is an amazing channel. It is my new favorite YouTube channel as of 2 years ago. They make these awesome videos about what's actually happening with mathematics. And yeah, the videos are excellent. If you ever want to think about being a math major, you need to watch 3 Blue, 1 Brown. Also Numberphile and a bunch of other ones. But 3 Blue, 1 Brown. Amazing channel. All right. And then These I want to hit later if I have time, but I need to tell you the most beautiful theorem after we do an example. The most beautiful theorem is Eulers' formula. We'll get to that after we do an example. After we do this, this is like a Khan Academy problem. There's two Khan Academy problems, one where you multiply, one where you divide. Show me now that you know how to do that. So let's multiply. Let's do it as a class. 8 times 4.
32.
32. Start your square bracket. Cosine of what?
5 pi over 4 plus pi over 2.
Okay, let's do some scratch work off to the side. So 5 pi over 4 plus pi over 2. I need to have like denominators, so I'm going to multiply one of these. 2 over 2. Okay, and that's now going to be 5 pi plus 2 pi, both of them over 4, and it simplifies to 7 pi over 4, which means I'm really doing cosine of 7 pi over 4. Okay, and I'm going to add that to I sine, same thing, 7 pi over 4. If this was in degrees, it would be even easier. You don't have to do fractions. You just literally just add them, right?
Wait, if it was in what?
If it was in degrees, like 180, so this would be 5 pi over 4. What is that? That's 100, no, it's 225 degrees. And this is 90. You do 225 plus 90. Done. There's no extra work. Let's try a dividing problem. W1 divided by W2. Well, what should my
2.
my magnitude be? My magnitude should be 8 divided by 4, which is indeed 2. Okay, set up your brackets. Cosine. Okay, what's our angle going to be?
3 pi over 4.
Oh, it's not. Oh, it is 3 pi over 4. Yeah, nice. You did it all in your head?
No, the work is right there. Just change it to subtract.
Oh yeah, so change this number to a minus sign and you get 3 pi over 4. Yeah, very smart. Good job, Eva. 3 pi over 4 plus I sine of 3 pi over 4.
Yeah. No, you didn't.
Done. If you can do that, you can do Khan Academy.
This is so.
So Khan Academy is easy. I think you guys can all do this in 5
This
minutes.
is harder than yesterday's lesson.
The concepts are hard. Like being able to rotate those in your head is hard. But as long as you know that if I multiply by W1, I'm stretching everything out by a factor of 8 and I'm rotating by a factor of 225 degrees. You can think about 225, I'm rotating everything like that. That's the hard thing. So this is the beauty. This is the stuff that isn't tested on Khan Academy, but I want you guys to know it. I want you guys to see it, to have a taste of how beautiful this is. So this is Eulers' formula. If you just type in Eulers' formula on Wikipedia, this is what pops up. E to the I theta is equal to cosine theta plus I sine theta, which is kind of cool, but it's not beautiful yet. I mean, it is beautiful to me, but it's going to get even more beautiful. The cool thing about this is we've been dealing with cosine of theta plus I sine of theta, and it took forever to write out.
Yeah.
It's condensed.
Oh. I like
Very
that.
nice and tiny. Okay. This is like it's almost, I'm starting to get goosebumps. We're going to have a drum roll here. What we had, though, is we multiplied this by its modulus, r. So now it's no longer Eulers' formula. We've changed it into something brand new. I'm going to multiply this whole thing by r. If I multiply the right side by r, I also have to do the same thing to the left side, and I get r. Take a moment, look at the top right of your paper on the front side. Flip over your paper. What is our logo?
Oh, that.
That.
Wow.
Okay, so we know where our logo is. Drum rolls ended. Let's talk about why this is cool. Why do these make sense? Why can I multiply this Z1 and this Z2 and somehow get the fact that I multiply the magnitudes and add the angles? I told you that, but I didn't explain why that works. If I use Eulers' formula, it does work. And in order to prove that this is true, by the way, you need AP Calculus BC, you need Taylor polynomials. Which is really cool. Like if you understand Taylor polynomials perfectly, which I still don't know, then the proof of this is really, really easy. But again, we're not in AP Calculus BC yet, so it's for another day. But let's talk about why it makes sense. So I can convert this now. I can convert Z1 using Eulers' formula. Who can do that for me? Who can convert this right side to the left-hand side for this Z1? Who can do it? You guys got this. It's nice and simple.
What do you want us to make?
So this needs to be something E to the I something. What goes out front? What comes right here? There's two blanks that you need to fill in.
R is in front.
R goes in the front.
Theta goes by the I.
Theta 1 goes by the I. There it is. We've converted it.
Oh.
Does everyone agree that that is the same thing as this?
Yes.
Nice and tiny and condensed. I love it. It's so easy to write. All right, someone else convert the next one. Quiet raise hand. Who's going to do it? Quiet raise hand. Chris, go for it. S E I theta 2. There it is. We've converted it. Now let's multiply it and see what happens. We can derive the formula just from Euler's formula. So if I do Z1 times Z2, I'm doing RE to the I theta 1 times SE to the I theta 2. Let's multiply those. So let's write it all out. We're doing RE to the power of I times theta 1 times SE to the power of I theta 2. Well, our rules of exponents say I do what to the coefficients and I do what to the exponents. Who knows this? I bet it. I can't give away too much. This is all the way back from Algebra 1 and Algebra 2.
E squared.
RS E to the power of
2. 3.
I theta 1 plus
I theta 2.
I theta 2. There it is. You literally add them. This is where it comes from. Done. I'm done. I have it finished. Because look back. R times S. Come back all the way up here. R times S. Look back over here. Add the angles. Of course, I could factor this out, and this could be I times theta 1 plus theta 2. I could factor out the I. I'm adding the angles. I'm adding the angles. That's where it comes from. All right, really quickly, we can do this. Z1 divided by Z2, it's going to be RE to the power of I theta 1. All of this divided by SE to the power of I theta 2. I need someone else, after finishing writing this down, to tell me what this is equal to in this form, in Euler's form. In our condensed form. Careful, not RS, it's R over S times E to the power of I theta 1 minus, I theta 2. And again, that power right here, this thing can be converted to I to the power, or if you factor out the I, it's I times theta 1 plus theta 2. That's our.
Wait, why are you multiplying the E?
Why am I multiplying the E? What do you mean?
Because it stands for Euler.
Don't say Euler. Please don't say Euler. It's Euler. It's okay. It's okay. It's a common mistake. Even Hollywood makes that mistake.
You can't even spell it.
I know you can't.
She
All right.
She's sold.
Are you guys ready for the most beautiful formula? Are you guys ready for this? Here we go. Let's go ahead and plug in pi to Euler's formula. Pi right here. Let's do it. Oh, what just happened? Let's do it underneath. This is the most beautiful formula. So R E to the I pi. Well, let's not do R. Let's just do E. Sorry. Let's get rid of E. R. E to the I pi. Well, what is that? I'm just substituting in pi for theta. Where's pi? Point to pi. Where's pi? Nope, that's pi over 2.
This way.
Yeah, there's pi. There's pi. Okay. What does that equal? When I plug in, not 0, it's not an imaginary number. Over here,
It's a real number.
it's a real number.
3.
180.
What is my unit? I don't have any number out here, so I assume it's 1.
0.
It's very similar to our warm-up. Come back all the way here to our warm-up. Our warm-up said over here,
2.
when I had 14 cosine of pi over 2,
0. 90.
this one was 90. Now I'm coming over to 180.
45.
So it would be
Let's go ahead and make a quick sketch, guys. Quick sketch. Pi is right here.
No, it's on the other side.
Pi is right here. What is this distance? What is this modulus? I assume it's a 1
90.
out front.
It's 90.
one.
So it's 1. This is a 180-degree angle. It's pi radians. And I have a distance of 1. So what is this number? What is that number right there? That complex number is
Negative pi.
negative 1.
Oh, it's the other way.
So, what we have said, and we're almost to that beautiful formula, is that e to the I pi is equal to negative 1. To get the most beautiful formula, just add 1 to both sides. Here we go. If I add 1 to both sides, make this nice and big because it is the most beautiful thing you'll ever see mathematically in your lives. E to the I pi plus 1 equals 0. Box this, double box it, say this is beautiful,
0.
this is beautiful. This is so cool. If I had a shirt, I would love a shirt like this. This has all of those crazy hard symbols. Look at this. You have an E in there. You have an I, you have a pi, you have a 1, you have a 0. Like the most basic and coolest math formula, all of these in one formula, all concise. You don't have any of this garbage, cosine theta, I sine theta, that is really long and hard to understand. All this boils down into this simple, tiny little formula.
I love
This is so cool.
Oh my god!
It's
Do they
beautiful.
make socks with that
Oh,
on
Dude,
there?
I'm gonna buy you.
I'm sure there are socks out there.
I'm gonna buy
This
you
is so
socks.
cool. This is saying I've rotated 180 degrees. I have a modulus of 1. That's what it's saying. I mean, it's saying a lot more than that, too. That's just one definition. Eulers. By the way, Euler, where is he up there? He is one of the most he's one of the most famous mathematicians. If you say Euler's formula, you usually have to say which one. He has so many formulas. I mean, this is the one that he's probably most famous for. Where is he on our wall of mathematicians? Where's Euler?
Eulers, what?
Eulers.
Eulers.
Oh.
Stephanie said
There
it.
he is. Leonard Euler, top right.
Oh, he's
He was the guy that did Bridges of Königsberg.
Leonard?
good.
Bridges of Königsberg. He did so much.
It's Eulers what? What's the formula?
Euler's theorem.
Play it again. Should I replay that?
Says
Yeah,
that.
replay.
Euler's theorem. Woo! All right. I would love to spend another half an hour talking about how you're actually multiplying by the conjugate whenever you're dividing. You're multiplying by the conjugate and then dividing by the absolute modulus squared. I don't think we have enough time, though. We get out of here at 52. Maybe next year. Maybe next year.